Hi, I am Yadagiri. In today's class, we discuss first law of thermodynamics in detail and state function as exact differential, path function as inexact differential, and also we learn reversible process, irreversible process, and we also try to prove, if possible, in today's class, work done in reversible process is greater than irreversible process. Okay, so first law of thermodynamics. Before we go into first law of thermodynamics in detail, let's recollect some of the basics. We have learned so far basics of thermodynamics, like the terms involved in it, and the process and properties. So those we have already covered. Now in today's class, we talk about exclusively first law of thermodynamics and subsequent topics like exact differentials, inexact differentials, and work done in reversible process is greater than work done in irreversible process. Okay, so now first law of thermodynamics. First law of thermodynamics. What is the first law of thermodynamics? First law of thermodynamics is stated as follows. Energy can neither be created nor destroyed. In other words, total energy of the system is total energy of the universe is constant. So energy is neither created by anyone nor destroyed by anyone. And what is the possibility? It only changes from one form to another form. One form to another form. Like using electricity in our homes, we are able to get light. So electrical energy is changing into electromagnetic radiation, light form. So that means energy is changing the form, but not created and also not destroyed. And total energy of the universe is constant because energy from one form is going to another form. In that process, there are no losses and there are no gains. And we try to give a mathematical equation for this. So the mathematical form is involving three important terms. Those are delta E, Q, that is heat, and W, that is work. This is change in internal energy. We will discuss what is internal energy is. Change in internal energy, and this is Q, heat, and this is W, work. Now we already discussed internal energy is a state function. It only depends on where it is. It doesn't depend on the history how it has reached to that state, and at the same time it is extensive property. It depends on the quantity of the substance. And the Q is also extensive property, but it is a path function unlike internal energy. And Q is same as heat. Sorry, work is same as heat. That means it is a path function and extensive property. So, and these three are related with the first law of thermodynamics as follows. That is, delta E is equal to Q plus W. So, in words, change in internal energy is sum of heat and work in the process. And here there is a sign convention. So now let's fix one of the process. Now let's take heat absorbed by system. Heat absorbed by system. So what is the sign here? System is gaining the energy. Therefore, it is a positive sign from system perspective. And W, let's say work done on the system. Work done on the system. So in that case, again system is receiving the energy, and therefore there also the sign is positive. And in both the cases, energy is received into the system, that is from heat as well as from the work. Therefore, internal energy increases. Therefore, this term is also positive. So let's see in a systematic way. Let's say this is a system. Now, into this system, heat is flowing. And also, we are doing the work on the system. As a result, what happens? Energy of the system increases. What is that energy? That energy is known as a internal energy increases. Internal energy increases. So this is how they are related. But it's not always the same factor, heat going into the system, work done on the system. Sometimes heat goes out of the system and work done by the system. So therefore, to know about this first law of thermodynamics, we must have a sign convention. And another thing here, the internal energy is a special thing. What is internal energy? Internal energy is energy of the system by virtue of its existence. Everything has some energy. From where that energy is coming? That energy is coming from its chemical nature, from its composition. Internal energy comes from chemical nature, basically composition. Is composition. So what does it mean? So any sample or any substance, matter for that matter, example, has many molecules. It's an ensemble of astronomical number of molecules. So molecules are always in motion. They are dynamic. They are not static. So they do translation motion. Therefore, energy associated with translation, that is translation energy, and they keep rotating. We also have rotational energy, and there are several bonds in the molecule. The bonds vibrate, so we have a vibrational energy as well, and electronic energy, because there are electronic levels, and we have other energies also like nuclear energy, etc. So all these things put together is internal energy. And internal energy absolute value is not possible to measure. So it's difficult to measure absolute value of the internal energy. So what we do, we know internal energy of the system is there in the beginning, and to that we are giving some energy in the form of heat or work, or we are extracting the work energy in the form of heat and work from the system. As a result, there will be a loss or gain in the energy of the system. That change we can measure. So how do we measure? we measure the internal energy changes in the form of heat and work. So that is why the relation is delta E is equal to Q plus W. Why here? Because it is the change that is happening because of the work and heat, and absolute values are difficult to measure. Therefore, you don't know the final internal energy, you don't know the initial energy to directly know the value of delta E. So therefore, E2 and E1, E2 minus E1 is delta E. It's not possible to know the E2 directly, and at the same time it's not possible to know the E1 directly. So therefore, measurement of internal energy absolute values are difficult. Therefore, we measure the changes in internal energy. Okay, now this first law of thermodynamics has internal energy term, heat term, and heat is associated with energy that is resulting from the temperature changes between the two things, system and surroundings. And what is the work? Work is actually energy that is associated with displacing the object. So the expression for work, now let's see what is the expression for work. Just now we discussed that work basically associated with displacing the object. Displacing the object. How? Let's say an object is here. You are using some force F. As a result, this object moved from this place to this place. So earlier it is at x1 position, now it is x2 position. And what is the displacement happen here? That is delta x, which is equal to x2 minus x1. The force used to carry out this displacement is known as a work, and the expression for work is W equal to F times delta x. This is the expression for work. So in thermodynamics, we mostly deal the gases. Let's talk in terms of values. Therefore, expression for the work is P external, that means the pressure we use, times delta V. So this is, what is the P external? P external is external pressure and what is delta V? That is volume change. Okay, how this equation has come? Let's see. Let's have a system, a cylinder that is consisting of some gas particles. So these are gas particles randomly, and this gas is sealed inside the vessel by a movable plunger. Let's say this is movable. This is movable and it has some area A. Okay, so let's take initially this has height of, let's say, x2. Okay, now what is the volume now? Volume is equal to area times the height x2 in the beginning. Now let's use some force. Let's use some force. What kind of force? We use a force from outside, external pressure. Some pressure, let's say, which is slightly higher than the pressure inside. So P external is P internal, slightly greater than or reasonably greater than the internal pressure. Then what happens? The plunger goes down because we applied pressure on the plunger by placing some weights. So then what happens? There will be a compression of the gas. Therefore, the volume decreases now. So this is a value, new value. This is initial value and this is final value. And area is again, this area is same, it is not changing. This is again same area, but what is changing here? What is changing here is the height, that is x2. So let's use here x1 for initial state, that is ax1, and here it is x2. Therefore now the value is equal to a times x2. So earlier we have a vi, now after the compression we have a vf. And what is the reverse is known as? The reverse is known as expansion. This process is from here to here is expansion. And when do we get expansion? Expansion is possible when P externally is smaller than P internal. Okay, so now we have a clear idea how things are happening. Now we know that force times delta x, that is changing position, is equal to W. Now we define something called pressure P, that is equal to force upon area. Force upon area. So that means the P is going to be here, that is P external is going to be, what is the force? The force we applied on the piston over the area A. So from this I can say force equal to P external times A. So now let's plug in this equation. W is equal to P external times A times delta x. What is the delta x? Delta x is the change in the position of the height of the gas column in the cylinder. So in the beginning we have x1 height, and the final we have a x2 height. And what is the delta x? Delta x is equal to x2 minus x1. That means final gas column height minus initial gas column height. Therefore we can say W work is equal to P external times A times delta x. Now A times delta x, that is going to be delta V. How? Let's see. Now A times, what is delta x is x2 minus x1. So that gives you A times x2 minus A times x1. So that is going to be, that is V final minus V initial. So therefore it is delta V. Therefore now I can write W is equal to P external A times delta x is there. Now I replace this A times delta x with delta V. So therefore expression is for work is P external times delta V. And here is one important thing we should keep in mind, that is sign convention. Let's go for the sign convention. What is the sign convention? Whether work done on the system or work done by the system, heat is going into the system, heat is coming out of the system, internal energy is increasing, internal energy is decreasing, that is sign convention. So now let's go to the conventions. Sign convention. Okay, now let's take work done by the system. Work done by the system. So that means system is expending its energy. Therefore, the sign is negative. Therefore, what is the expression for work now? Work is equal to negative P external times delta V. Remember here, when system does a work on the surroundings, what will happen? Now let's take in a tutorial way. Now let's take gas inside the cylinder is system. Now when does the system does work? When system does work? When P external is smaller than P internal. So this is P external and this is P internal. So now what happens here? There will be a increase in the value. That means V2 is greater than V1. That gives delta V is equal to positive, because bigger number minus smaller number is a positive number. So P external is always a positive number. Here we got delta V positive number. Therefore, work done in expansion or work done by the system is always negative. Okay, that is W equal to negative P external times delta V. Now, work is always a positive quantity. That's why we have to maintain this sign convention. So for expansion work, it is negative, because P external times delta V is a P external times delta V should become a positive word. Right. Now work done on the system. Work done on the system. So here you may be having some doubt. So P external times delta V is positive, and before that we have a negative sign. So this term is W, work, and before that we should have a negative sign. So negative times negative is positive. So how it is, I will explain further before we go into the work done on the system. Now we got W, that is P external times delta V. So P external is positive term, delta V is positive term, and we have a negative sign here. Therefore, it is a negative term. And W is in the sign convention of work. We have taken a minus value, negative sign. So this number coming from this expression and the sign convention of work, making the work as a positive quantity. Now let's go for what is this work done on the system. When work is done on the system, what happens? There will be a compression. So the final value is smaller than initial value. So V final is smaller than V initial. Therefore, delta V is negative term. When delta V is negative, what happens? Negative P external times delta V is also a positive term. So therefore, to make work positive, we should take work sign also positive sign. For expansion, this expression is giving a negative value, and we know work is always a positive quantity. Therefore, to make this negative value to positive reporting, we must use a sign convention of negative in the expansion work, that is work done by the system. Okay, now heat. So when heat goes into the system, that is Q is positive. When heat is coming out of the system, then Q is negative. Remember, heat is a process. Now here, if you remember correctly, when heat is going out of the system, that is exothermic. Exothermic. When heat is going into the system, that is endothermic. Endothermic process. So this is about heat. So these two things, heat and work, results in the change of internal energy. And what is internal energy? Internal energy is energy associated with the virtue of substance on its chemical nature and composition. And we already discussed that exact magnitude is not possible to measure, so that means absolute value. So what we do, we always measure the delta E. Now let's go further. What is that? State functions, path functions. What are the state functions? The functions, those do not depend on the path or the history how they are coming to that place, that state. Those are known as state functions. And those functions are properties that depend on the path. The history how they have reached that state are known as path functions. And generally, it is always state functions are exact differentials and path functions are inexact differentials. So let's see what is exact differential and inexact differential. So before going to that one, let's check something. Temperature. Temperature is a state property. How can you say it is it's a state property? Let's take our town as an example. Here, the temperature is same for anyone reaching this state. So that means the path followed by different people is not relevant to the temperature in this town. Therefore, what we can say, temperature is a state function. It doesn't depend on the history of how you have come to that state. So all people, locals and outsiders, will feel the same temperature. Okay, but work is a path function. How is path function? So you have done a work, basically, let's say, in a process where you have brought the same volume change. Let's talk about two processes in two different ways. Let's say both are expansions. So this is initial volume Vi, and here also Vi, and we have a P external here. Let's say P external is smaller than P internal. So then what will happen? This is now this is higher than P external. Therefore, there will be some kind of expansion. So this is the new position of the plunger now. So then what happened? This is the volume change, delta V. And the same thing, let's say, same volume change is achieved here. But this time, let's keep the external pressure 0. That means here, the expansion happened against the vacuum. So then what happens here? Work equal to, we know the work expression. What is that? Negative P external times delta V. So here delta V is a finite number. And here also it is a finite number. So at the same time, P external is, some pressure is there here. So P external is also some number. Therefore, P external times delta V is actually there is some quantity, there is some magnitude here. But what happens here when you have a expansion against vacuum? the P external is equal to 0, therefore work is equal to, we know the expression for the work, that is negative P external times delta V, that is going to be negative 0 times delta V. Therefore W equal to 0. The same state we have reached in both the processes. In the first process there is some work done, in the second process or second path there is no work done, though we reach the same state in both the cases. So by this example we can say that work is a path function. Work is a path function. Now let's go to the again first law of thermodynamics. So what is the first law of thermodynamics? That is delta E is equal to Q plus W. Now, and we know delta E is a definite quantity and a state function, and delta E, now I am using the new word exact differential, which is applicable to state functions. W and Q are inexact differentials because they are path functions. This is exact differential, and these two are inexact differentials. We shall discuss them in detail now. What is exact differential? Inexact differentials. So exact differential is something, integration of exact differential over range u1 to u2, let's say internal energy, some people use u as a sign for internal energy, that's going to be u2 minus u1. So that means basically it is equal to delta u. This is for state functions. Which are exact differentials. Now for path functions, let's take heat. This is not equal to Q2 minus Q1. The same way for work also, it's not equal to W2 minus W1. So this is known as a inexact differential and path functions. Now, one more thing we learn, that is reversible paths, a path that happens very slowly. Why? Because the process that is happening against opposing forces are such that both the forces, opposing forces, have a very little difference. Let's take the example now. Same cylinder example containing the gas. P external, that is external pressure, almost is equal to P internal. So that process happens much slower, and at the same time we can reverse this process at any point of the time. Therefore this is known as a reversible paths. And there is other paths where you can abruptly bring the change. How? The P external is quite a different value than P internal. Maybe it is bigger than P internal or much smaller than the P internal. So when P external is not equal to P internal, then change is going to happen very quickly. So when P external is very higher than P internal, compression happens quickly. When P external is much smaller than the P internal, gas pushes the piston quickly and there will be expansion. So those things will happen. Now let's go for a work done in a reversible path is always greater than Irreversible path. What is irreversible path? Where opposing forces are not having the closest values. They are quite different in magnitude. So therefore the process happens quickly, and those processes are known as irreversible processes. Okay, so exact differentials, inexact differentials we covered. And what are those? State functions have the properties of exact differentials, and path functions are inexact differentials. Okay, so we will prove in the next class that the work done in reversible expansion or in a reversible process is always greater than the work happen in irreversible process. And also we prove that work and heat are path dependent properties, and internal energy is a state property. So state properties do not depend on the history of how they have come to that state, and path properties depend on the history how the process happened. So path properties, for example, W, when it shown as a differential work, that is work, it's shown as differential dW, it must be shown with hyphen on the top, so cross. So therefore this is indicating path property, say path function. One important thing, we must learn it. Okay, so this is today's class. We have covered some things, and we'll try to do some problems. What are those problems? Let's take a system is doing work on the surroundings 20 kilojoules, and it is absorbing the energy of 50 kilojoules. So 20 kilojoules work done by the system, and 50 kilojoules heat absorbed by the system. Absorbed by the system. Then what happens to the system now? Let's use the first law of thermodynamics. What is that? Delta E is equal to Q plus W. Okay, here work done by the system, therefore it must be a negative sign, therefore we should take negative 20 kilojoules. Here system is absorbing the heat, therefore we should take Q as a positive number, therefore this 50 is a positive number. Now let's substitute here. Delta E is equal to Q, that is 50 kilojoules plus, and what is the work done? 20 kilojoules by the system, that's why negative sign, therefore it is 50 minus 20, that is going to be 20 kilojoules positive. So that means basically here the system is doing the work with the 20 kilojoules on the surroundings, taking 50 kilojoules heat from the surroundings. Basically it has taken 50 and given away 20, it is still retaining 30 kilojoules of energy. Because of that, the temperature increases. Remember, we discussed in the previous class, internal energy is purely a function of temperature. The temperature changes, internal energy changes. When heat is absorbed by the system, when work done on the system, its energy increases, therefore temperature increases. This addition of 30 kilojoules of heat energy to the system results in its temperature rise. So the next class we shall discuss about, in the next class we shall discuss the problems associated with first law of thermodynamics, and also in details about the exactness of differentials. What are the rule for exactness of a differential, and is there any better criteria in a mathematical point of view to know whether a particular differential is exact or inexact. And thank you, and this is the class for today, and thank you very much.